Hello, welcome to our today's webinar on 6G. My name is Christian Wietfeld. I'm the head of the Communication Networks Institute at Technical University of Dortmund, and I'm also involved in the 5G North Rhine-Westphalia Competence Center, which organizes this session. Today's title is 6G Challenges and Solution Perspectives, Gazing into the Crystal Ball, and I'm very happy that four distinguished panelists have accepted to provide a talk today. But before I would like to introduce our panelists in more detail, I will just shortly set the scene for this session. This session is embedded in a complete week dedicated to 5G. On Monday, we had a first session, a hybrid conference in Düsseldorf with speakers on 5G campus networks, network slicing and security. And this was basically the kickoff of this week on 5G. Yesterday, there was a challenge on, there was a session on 5G in the industry. Today, we have our 6G session, and in the subsequent days, we have additional offerings and webinars related to 5G. Today, we are focusing on 6G, and there's obviously the question, why should we talk about 6G when 5G has just only started to become a reality? And when we look into the history of mobile networking generations, we can see that every decade, a new generation has been launched. It starts with 2G GSM in 1990 and so on. And so when we consider that 5G has been introduced since 2020, it seems to be already a natural law that there will be something like 6G in 2030. So this is something we learn from the past, and when we also learn how long these generations are active, we can see that we are looking into the future of 30 years of a future mobile network generation. But this sometimes creates confusion because users especially might be confused that once they have learned about 5G, there's something new coming up, but it's really a long distance walk that we are, or long distance run that we are entering here, while the users focus on 5G. The networking technology researchers are already looking into the next generation, the 6th generation. And when we look into a generic timeline of mobile networks, considering the launch year and some future point in time, 10 years before the launch year, the technologies triggers from research are generated. Then first discussions in standardization will take place, so-called study items. Concrete specifications will be developed, concrete products, and then there will be a launch. And after that, around 20 plus years of usage of this technology and further evolution. When we map this timeline, this generic timeline on 6G, we can see that we have entered the phase in which technology triggers from research are being generated. And essentially also fundamental patterns are being generated well ahead of the standard specification phase. So right now is a time to generate the fundamental ideas for the 6th generation. And that is why we are focusing this session today on these potential future perspectives of 6G. But obviously it's a long-term perspective, and therefore we have to ask ourselves, what are the potential 6G drivers? And many drivers have been mentioned, and we will learn a lot more about these potential drivers in the subsequent panel talks. Therefore, I would like to just shortly mention some of them. It is, for example, mission critical timing and reliability, wired equivalent behavior, even in the most challenging environments, disruptive concepts of communications beyond the 4G, 5G toolbox, new applications, the leveraging of terahertz spectrum, improved sustainability, new security concepts, ultra low power and wireless energy transfer, as well as convergence and interoperability, with 6G, including maybe Wi-Fi, LoRa, and satellite evolutions, and also more openness leading to more flexible and faster innovation. And many more ideas have emerged, and therefore in this panel session, we would like to discuss some of them. Obviously, 6G has become a hot topic around the globe. It all has started already around 3 years ago in April 2018 with the 6G flagship project launched by the University of Oulu in Finland. But this flagship initiative has reached far beyond Finland. It has a European and even international reach. Starting from that, many other initiatives have been announced in all areas which focus on the development of mobile networking technology. In Germany, a milestone has been reached in August with the introduction of the 6G research hubs in Germany. And there are 4 of them, and one of them, the 6GEM research hub, is particularly interesting from a North Rhine-Westphalian perspective because the major universities working on mobile networking technologies are involved in this 6GEM hub, and also myself and some of the speakers of today are involved in this hub. In addition to this research hub, which has mainly academic partners, there will be upcoming calls for joint industry and academic projects in the upcoming years with a considerable volume, which shows the importance of this area, also from a German perspective. In the 6GEM hub, we will address many of the topics that have been also mentioned before as drivers for 6G, like the radio access technologies, networking technologies, security and safety, terahertz communications, and joint communications and sensing. But a particular highlight of this hub are the diverse test fields for instance, related to autonomous driving, high-speed logistics, and rescue robotics. When we discuss today in the panel, there are some open questions which might be addressed. For example, which will be the disruptive, potentially even game-changing 6G developments? How will openness, flexibility, efficiency balance with performance of the system? What will be 6G success factors and which pitfalls should be avoided? And finally, how can Europe, Germany, and North Rhine-Westphalia take their chances in the global race for 6G? And to discuss these topics, we are very happy that 4 distinguished panel speakers have accepted to provide the talk, and I would like to introduce you to them now. First of all, there's our first speaker, Mehdi Bennis from the University of Oulu, as has been mentioned before, the initiators of the 6G flagship project. He's also a research fellow of the Academy of Finland, and he will talk on semantic communication meets machine learning, Division X. The next panel speaker will be Ingrid Moermann. She's leading a group of 30 researchers at imec, which is also affiliated with Ghent University in Belgium. And she will talk on interoperable wireless time-sensitive networking towards 6G. The third panel talk will be provided by Gačanin. He's from RWTH Aachen, and he's also the coordinator of the 6GEM Research Hub, which has been mentioned before. He has been previously in industry with Nokia, and he's a serial inventor with over 90 patents, and he will talk on the wireless perspective of 6G, a programmable digital sense service space. And finally, Thomas Kaiser from the University of Duisburg-Essen, and also the speaker of the Collaborative Research Center Marie, will discuss terahertz for 6G. Thomas Kaiser is also a well-known entrepreneur with several startups launched in the past. So I hope you will find these upcoming discussions fruitful, and I would welcome again also the audience. And I would like to invite the audience to post questions with the question and answer feature of Zoom throughout the complete session, and we will then take up these questions in the joint panel with the questions and answers Q&A from the audience, and this will then conclude our session. So we will have around 2 hours of a session addressing these topics. So after this introduction, I'm now happy to pass over the screen to Professor Mehdi Bennis. And yeah, Mehdi, it's your floor now. Thank you very much.
So please let me know when you start seeing my screen.
Yes, it's the screen is visible.
Very good, very good. Okay, great.
Thanks.
So thanks again for inviting me to present to you a vision, which is called Vision X, which is about the marriage of 2 transformational technologies. On one hand, of course, semantic communication, and we will see what we mean by that, and also machine learning, but we will be a bit more precise what we mean by that. So as we all know today, and again, we started, Finland was the first country to look at what 6G may be, and of course there were many visions that followed. But in short, we can say today that most of the vision are typically about adding more data rates, high reliability, high connectivity. This is, I think, taken, I don't remember which one, but this is from the Hexa-X, essentially talking about concepts like bridging the biological, physical, virtual world. Federated maybe is on the line today. He also actually even challenges the 6G vision, which I agree with him, but we can leave that for a further point. Essentially, that some of the requirements are actually not needed in 6G. So in other words, we should not really keep just looking at higher frequency bands, maybe higher data rates, but we should try to maybe reverse that paradigm. This is the Qualcomm vision again. This is the Docomo vision. So all the visions today are basically taking 5G and just adding a couple of zeros and basically trying to, justify the need for 6G. So in short, 6G is really about bridging the physical, digital, and biological world. The current visions of more bits per second, more bandwidth, more densification of base station, the better, are actually not sustainable in the long run, right? Taking 5G requirements, for example, in the case of ultra-reliable communication via packet error rates, and just multiplying this by 2-fold, 3-fold, 5-fold, are actually myopic approach in the sense that actually you do not need to satisfy those extreme high reliability, for instance, in robotic applications. This is something that Professor Fedvais keeps mentioning a lot, and actually is right. Then, of course, despite the huge progress in AI, we need to be a little bit modest and realize that actually current AI solutions are brittle, energy hungry, and just curve fitting. They just interpolate, okay? And then you have, of course, Open RAN, joint sensing and communication. And some people say that 6G is whatever we will have in 2030, which is a statement which is a little bit annoying, right? And should be annoying to all of us. All this points to the fact that 6G today is nothing but an incremental evolution of 5G. And this is where the new vision, called Vision X for a better word, try to flip the paradigm of current 6G approaches by asking a number of questions. So the first one here is, can we transmit less while achieving, of course, the same performance, and start relaxing some of the stringent requirements in certain applications, not in all applications, in some of them, because there are actually many, right? Number 2, I think it's quite, it's a consensus today that 6G will be communication for machines as opposed to for humans, right? So, of course, we talk about human-machine interaction, collaboration. In other words, can we actually learn from us, the humans? And for that, there are 2 cognitive modes, which are referred to as System 1, System 2. And I'm happy to walk you through this because this is a very fascinating approach of trying to solve 6G. So what's System 1? System 1 is essentially our brain has this very fast reflective reaction, right? Essentially is able to if it has seen a previous experience before, it knows how to replicate, right? As opposed to that, you have what we call System 2, which is the cognitive task of the brain, which is used to reason, which is used to plan, which is used to deal with long tail problems, situations that have not been seen before. And that's actually what we need to be now incorporating in our networks, 6G in particular. So I believe actually the solution to unlocking this step function from 5G to perhaps we should call it real 6G or 7G, I don't know anymore, sits at the intersection of 2 revolutions. So the first revolution, essentially, of course, is in communication. So people, of course, have been talking now for 1 year, 2 years now about going back to fundamentals of Claude Shannon paper, 1948, where he laid down the fundamentals of communication. So there is this level A, level B, level C. Level A essentially is all about, transmitting a packet from a transmitter to a receiver, how to best encode it, right? And then transmit over a channel, and then you try to reconstruct exactly the same packet, right? It turns out, of course, that even actually in the paper, Shannon mentioned that there is no need for meaning, there is no need for context, there's no need for structure, no need for memory. Just throw away all that important information. So this is level A. It turns out, even in his paper, of course, there are two levels, level B, level C, referred to as semantic. So how do you actually extract the semantic information from your source data and communicate to the receiver? That's level B. Not only that, because that's not actually enough, you need to make sure that the receiver is acting upon the semantic information that he's receiving. Okay, these are two fundamentally different than level A. Okay, and then of course here what we are trying to do in level B, level C is bring back semantics, bring back structure, because real world phenomena, the world around us is full of structure. So the idea is to leverage that structure and imbue it in our communication to be more efficient, more data efficient, more robust, and all the other requirements, okay? And here, essentially, communication is different. Here, communication is no longer a reconstruction task, because here it's all about X equals X hat, right? Here, essentially, the communication is an immersion property via the interaction of a transmitter and the receiver through sensing, through actuating, and being grounded in the environment. Essentially, in other words, you need to model this as perhaps people are familiar with multi-agent interaction, right? Where agents now are modeling each other, right? And reasoning about the intent, belief, knowledge of the other counterpart. That's essentially what we try to do. Of course, it's very intuitive because essentially that's how the brain works for us humans, but this is not how networks are optimized today. Number two, AI, of course. So AI, we need to be, again, modest, as I was saying. We need to understand the limitations. So AI today is obsessed with accuracy. We just look at, winning competitions and outperforming baselines, but we need to pay attention, of course, to the energy bill, sustainability, right? We live in a climate change world. But more importantly here, more technically, as I said before, current machine learning, which are system one approaches, are brittle. They don't generalize to out of distribution, meaning you train them in one environment, you deploying them in another environment, they just fail. Okay, so think about autonomous vehicles or other safety critical applications. Federated learning, which my group actually helped, contribute quite extensively. We realized later on that just the first baby step towards intelligent systems. Why? Because essentially they are just function approximator. They are interpolating, input output. Essentially just learning correlations in the data, and then we talk about small data versus big data, but we fail to see the point. Here, the point is not really about the quantity, but about the semantics or the usefulness of the data that you have, okay? And of course, current approaches, as I said, lack reasoning. They don't extrapolate. We need extrapolation as a key ingredient and imagination or counterfactual. So what we propose in this Vision X, of course, is to come up with new desiderata. Think of these are new ingredients that we need to keep adding in order to satisfy the system to approach coming, by the way, from machine learning, right? So number one, of course, the representations that we need to learn from the real world must be, of course, function of the data, right? Number two, they need to be minimal in the sense that they are compressed representation of the source, right? While keeping in mind that actually that compressed representation has to be sufficient and in the sense that the receiver has to understanding and act upon it. Number three, invariance. This is a key part here. Of semantic information, essentially to learn what's invariant in the network, right? Is it, so for example, is it robust, right? To say, if I take an image, right, you have translational invariance, right? You have a network, you have permutation invariance among the users, right? Can we actually learn this invariance? Or if we know it, let's at least encode it into the neural network structure, right? These are called inductive biases. Number four, we need to be able to decompose the knowledge, right? We talk about disentanglement here, essentially just taking an image or a video or whatever process you have and try to deconstruct it in terms of key building elements. And those are the pieces of knowledge that we'll try now to generalize to different environments. Number five, I think it's very clear here that we need to move away from learning statistical correlations, which actually is what Shannon communication does, but interestingly enough, is the same problem or issue in machine learning today. We just learn correlations. And we know from school that causality is really not correlation. Emergent here in the sense that sometimes this representation that are learned between a transmitter or receiver or among multiple agents are emergent properties, meaning that they are not fixed from the beginning, but emerge via interaction among agents. Okay, so think of it as a piece of Lego, essentially, right? We want to compose these Legos so as to build different castles, houses, and so on. Okay, so here the new objective is no longer just to do what we do today in the whole, at least communication, let's say, society, which I'm part of, right? Just, instead of just focusing on these two desiderata here, right? Learning representation that satisfy 1 and 2. No, we need more. We need the 6 desiderata, right? And then, of course, we need to fix the target. So what is the target? Is it to train a model? Is it to do inference? Is it to do intent prediction? This is actually a little bit more kind of comprehensive than just doing 1 and 2. And I hope the message went across. So the problem is today, everything is called semantic communication, and I actually expect that this will be kind of becoming the new buzzword in the community, perhaps because we lack, new concepts. Of course, semantic is kind of easy comer here. So what I'm gonna do now is try to, make us understand the difference between what people call today semantic communication versus what should be the real semantic communication. Because in fact, you can see from the literature, at least, some people refer to it as goal-oriented communication. Some people use qualitative communication, semantic even in power communication. So sometimes you get a bit confused. So what really are we talking about? So that's my goal today, okay? So what I'm gonna present to you in short are 2 concepts. One is called System 1 semantic communication, and I'm using this terminology to disentangle essentially what is already done today, I would argue, versus the next frontier, which is System 2 semantic communication. So what's System 1 semantic? System 1 semantic communication is really about learning in what we call the data space. Okay, think, for example, as an example, this is a VR user interacting with the scene, and of course now you want to make sure that the field of view or the scene with which the user is interacting, right, is the one that you will be basically provisioning resources, and then you can maybe blur out the rest, or maybe not necessarily to serve him with both, say, ENBB and URLC. This is a System 1 semantic communication, because essentially it's based on the 2 desiderata, meaning the minimality, right, and the sufficiency, because they're just compressing in the data space, right? And then the task here is to reconstruct, meaning now you want to transmit a packet from a transmitter to a receiver, and you want to fully decode it. But the problem is here, in semantic communication, you don't have to entirely decode every single bit of your packet. What is more important is, keep level B, level C in mind, you need to decode the semantic and of the intended message and then act upon it. And this is where now System 2 semantic communication comes into place, which actually builds on System 1 semantic communication by adding the other missing desiderata. And here the tasks are not interpolation tasks. They are not reconstruction tasks. These are tasks, for example, to reason, right? Extrapolation, imagination. So imagination, think of it as a digital twin. So digital twin is a concept we keep hearing about all the time, right? But what does it really mean? Digital twin is all about 2 agents, and every agent has a model of the other agent, and then try to predict the behavior or the action or the path of the other agent till they cooperatively, for example, reach, let's say, consensus or other, right? So here you could now try to go a little bit beyond kind of state of the art now, right? So now you could think about now trying to invent new communication protocols among agents, right? So now these are, let's say, in a factory, and you don't want them to use 3GPP language, which is actually hard-coded, it's human-based, right? Now you want to try to learn a new communication language between robots, okay, based on the sensory motor, again, interactions, right? And then, of course, what matters here is 1, what's the vocabulary they will use? 2, what is the ordering of the message that they will communicate to one another, right? And to achieve a task X. Task X could be navigation, collaboration, whatever you have, okay? 2 here, and there are some early works, actually, even in Nokia here, trying to, model the kind of current networks. You have a base station here, and you have users. Base station is a teacher, and the users here are learners. And the idea here is that actually the base station is acting as a teacher, trying to teach the signaling to how the learners locally should transmit. In other words, let's come up with a new 3GPP type of protocol that will outperform the current one. And I think it's a very good idea. Here we should not be too, too excited in the sense that we always need to keep into account the backward compatibility. But my point is actually we could definitely try to apply this new concepts which are clearly beyond 5G or beyond the current 6G to look at new scenarios, and then you could add now even kind of a human in the loop. So now you have, for example, a human teaching a concept to a robot, or maybe you have a robot here trying to infer the intent of the human, right? Visually from a camera, infer the intent, and then either help him or assist him, right? So this is not about Shannon. Shannon is all about, again, copying one input from one transmitter to the receiver. Here, no, inferring the intent. That's a much more difficult problem than just, input-output map, right? And again, my point here is things like digital twin, resiliency. Everybody has a different definition of resiliency. Here, resiliency is the ability to generalize to a new environment that you have not seen before, okay? This is the idea, because here you are leveraging the knowledge that you have acquired in different say environment, and then I put you in a new environment. You still need to operate, and that's not how we actually use machine learning today. Arguably, all our say machine learning papers fail as soon as you change the environment. Okay, so in short, what's Vision X? So the idea is, on the machine learning perspective, we want to depart from learning in data space. So just keep in mind, you have the data space, and then you have a semantic or abstract space, right? So the data space is where you have the pixel, if you're an image. Now, of course, if you're in wireless communication, think of it, this is like a channel state information, but it could be anything else, right? Towards learning, discovering representation of the real world. So think of it as a factory, any environment you have in mind, right? With objects, agent interactions, right? And this is what gives rise to the system 1 versus system 2 semantic communication. Now, on the communication side, now we want to depart from, again, Shannonian type of communication, meaning it's a reconstruction task where the goal is how to best encode the data, okay, to be transmitted to the receiver, towards a new kind of, definition of communication, because here what matters essentially is to satisfy level B, level C of cloud channel paper, or where agents actually are inducing behavioral change or impacting causally the other agent and vice versa. And that's the concept of semantic communication that we're aiming at, okay? Now, the advantages are so many, because now you transmit actually less and achieve more, because again, here, I don't want to, decode with super high reliability all the bits that you transmit to me. I don't need to, as long as I infer the intent. And guess what? Sometimes you don't need to communicate to me because I already have your model, so we don't need to communicate. We only communicate maybe to revise our model, because essentially it's a kind of imperfect model. So, we need to coordinate every now and then. 2, is much more reliable, and I think you see why. More energy efficient, more sample efficient, not just throwing more big data and train, because sometimes, and this is a key point here, the knowledge is not in the data. Sometimes this is actually the key part to keep in mind. And of course, intelligence, I think it goes without saying. So in short here, what I'm kind of pitching for, and I've been doing it for a while now, is, we need to now not talk about 5G plus AI, that's 6G. No. We need a revolution within AI, okay? And there's a system 2 part of it, and a revolution within communication, and that's semantic communication. And to me, these are the 2 foundations which are missing in the current 6G visions, because the current 6G visions are basically based on level A and system 1 machine learning. And of course, this is a vision. There's a lot here, because you definitely require multiple disciplines. You require him from logic to category theory to control, of course, information theory, as we know how to do it, to machine learning, right? It's a big vision. It's a big vision, of course. And this may explain why, of course, this self-critical analysis of mine, because essentially we missed the point. But I think it's not too late to try to reverse course of where we should really focus, because this is definitely going to be a step function. And with this, thank you very much. So for those interested, there is a technical paper detailing a first step towards what we mean by semantic native communication with contextual reasoning. I invite you to take a look at it. And then the more vision, a 30, 40-page vision articulating what you just heard, will be hopefully finished very soon. And then, will be shared with all of you. Thank you very much.
Thank you very much, Mehdi. That was a great talk, and really this shows visionary concepts. And actually, you on your previous slide, you hinted to the, I think it's a LinkedIn article.
Yeah.
At least I read it on LinkedIn, and I can only really recommend it. It's really a very good analysis of, and as it's mentioned, a self-critical analysis, which I also felt as a self-criticism for my own thinking of what 6G can be, because I think we are somehow in the danger that we simply go on as previous at the previous generations, and we miss a chance for some disruptive ideas. Yeah.
Absolutely, I think we missed it, but I think this is not going to happen.
So
we can discuss later.
Okay, so at least we can mingle in some disruptive contents into 6G. So thank you very much for this talk, and I think we just go to the next presentation and enter the more detailed discussion later. And therefore, I would like to invite Ingrid now to share the screen. Thanks a lot, Mehdi, for the first talk.
Yeah. Hello, good afternoon. Can you see my screen in presentation mode?
Yes, we can see it. Yeah, yeah.
Okay, great. So in that case, I can get started. So first of all, thank you very much for being invited here and for the possibility to give a presentation. I'm afraid my talk will be a bit different than the previous talk, and maybe that's good. No matter which communication technology, which generation, 4, 5, 6, maybe 7G, no matter how capacity and speed, which is a bit the factor X in the previous talk, I think until today, we are still not able to offer quality of service, to offer time-sensitive communications with very strict guarantees in a shared wireless environment. And this is what my talk is about. I'm afraid I'm not so intelligent as a previous speaker, so my talk is not about AI and machine learning, although I think we share some of the concerns, and I'm sure that the AI can also support the time-sensitive networking. But okay, let's get started. So first of all, why do we need time-sensitive networking? And so there are many demanding, time-sensitive applications going, and these are just a few use cases that are listed, going from Industry 4.0, the audio, video, haptics, and then the AR and the VR. I think these use cases were also mentioned in the previous talk. Oops, what's happening here? And then if we put some requirements, and in this presentation, we are mainly looking at latency. So this is the axis here, but you can also see what are the requirements in terms of throughput, and sometimes you also need mobility. And okay, requirements can be quite different, but what we also observe, and maybe I can show you the next slide, that actually the applications that require low latency are not necessarily the ones that need high throughput. So actually, it's a bit the same what you could see in previous slides, but now you can see here latency versus throughput, and actually this area is very important. So I would say not a very high speed, still quite high, could be up to 10 or up to 100, but maybe not the highest speeds are most important. And but that's actually what I wanted to say. So what does time-sensitive mean? It means that you want to offer deterministic networking, although wireless is by definition not deterministic, and the communication is driven by end-to-end quality of service demands by applications. And what is deterministic? It can have many metrics, many KPIs. In the first place, it's latency, because if you meet latency, the guarantees, you actually meet many of the other KPIs. If you succeed to transport information from one place to another place in time, then you probably meet reliability, you meet throughput, availability. Has also to do with is the service always available, coverage, whatever. So this is what we mean by deterministic quality of service guarantees. And if you want to set up a system, you need some major technology already today, and all the innovation is mainly in the digital domain. On the other hand, a lot of the new generation, they focus on high capacity, pushing technology limits, which is also important, of course. But what I wanted to say, that quality of service, from what we see here, is not necessarily the same as high capacity. You could, of course, offer 10 times, 100 times more capacity than needed. But then you have another issue, that something that is often overlooked, that you should also take into account efficiency. So spectrum, cost, energy, whatever. Okay. Another thing, yeah, we are talking about wireless, but you never have wireless without wires. So in the end, a communication link, it's not just the wireless access. You need to have end-to-end, also the infrastructure, and quality of service needs to be verifiable, meaning you should be able to measure the performance and take corrective actions if needed, which is going beyond the typical promise of quality of service. You can do quality of service scheduling, but you are never sure that the quality of service is really achieved. So verification is very important. If you cannot measure it, how do you know that you got the quality of service you need? And it should not be a kind of aggregated quality of service, which is still the main mechanism today. There are some classes and there is some notion of aggregated quality of service. This is not enough for deterministic networks. It should be possible to do that at a lower granularity per flow and end-to-end, not just in the wireless link, not just link level promises, but true end-to-end between the end processes of the application. So coming to the time-sensitive networking, so what is it? So in the end, main focus is you want to offer an end-to-end bounded latency, and you have to do that over the wireless access, which connects the devices, and you still have the wired infrastructure. And we need, in the first place, what do we need? We need synchronization of all devices, meaning that there is a global notion of time, not only in the network, also in the end devices. The next thing, you have to be capable to schedule whatever resources are available. And you have to do that across the wireless and the wired network to ensure that the service is delivered in time. As I said before, it's not sufficient to promise quality of service or to do some scheduling. You also need visibility in the network. You should be capable to monitor the service that has been delivered. And based on that, you also have to react. And here, intelligence can come in. It's better to not react when it is too late. It's better that you can predict and that you can anticipate and that you can do proactive configuration. So this is the general concept of time-sensitive networking, and it should, oh yes, and something important that I forgot, and again, I see a link with the previous talk. You need some kind of a rich application network interface, because how does the network know which kind of service that needs to be delivered? So this could be a kind of semantic interface, as was discussed before. So how, and here I will just show you an example. This is perhaps happening. It's in 5G beyond research of things that are already happening today, but that can enable lots of more innovation in future in view of time-sensitive networking. And first of all, in order to do innovation, of course, you can do a lot of concepts on paper and in simulation, but time-sensitive is also so much depending on the hardware. So open prototyping platforms are also important. And here I will just present you one possible platform. It's a platform that we are using for our research. It's a fully open platform. It's free. We have thrown it in the public domain. It's an open source project. Anybody can use it. And the nice thing, it's Wi-Fi. It's not cellular, it's Wi-Fi, but in the end, it has a physical layer. It's open, you have full freedom. It's also OFDM based. Wi-Fi also has OFDMA, so it's a bit comparable. And nice thing, it's compatible with Linux. You can use it as the way you are used to use it in off-the-shelf devices. And it allows you to do innovation, to do customization, to add special features, which we're of course doing, as I will explain later. We added some time-sensitive features, and that's it. We are now also working on an evaluation kit. So if other people want to help us to innovate and do more sophisticated stuff, you are welcome. But okay, let's have a look at the synchronization, because that's a difficult thing. You cannot offer time-sensitive services if your devices are not synchronized. And we have used our open Wi-Fi platform. We added some time synchronization feature. We are able to add hardware, very accurate hardware timestamps. And in this way, we have synchronization accuracies in the order of microseconds, end-to-end, all devices of the network. This is single hop, just a Wi-Fi link. But the nice thing, Wi-Fi is a natural extension. It's an IEEE standard. Time-sensitive Ethernet is a very important networking enabler for time-sensitive network. It's actually the first network technology that offers these features. So we did actually a natural extension of the Ethernet, having similar features in the Wi-Fi, and even end-to-end over multiple hops, wired, wireless. We can have accuracies in the order of a few microseconds. If we try to do that today with off-the-shelf devices, it's impossible, where you see orders of magnitude lower synchronization accuracy. That's first thing. So seems like we already solved. No, I think it's a good enabler. We are on the way, but it's a first indication that innovation is possible. Next thing, scheduling. Again, we did some extensions on top of standardized Wi-Fi. We added hardware queues. We can apply for each queue dynamic channel access parameters. We can dynamically assign flows. We can do time-aware traffic shaping. So actually we have a bit of the timed gates concept, the same as you have in a time-sensitive Ethernet switch. And we are able to schedule uplink and downlink and organize the traffic. All this can be done. And this, we can do that jointly with Ethernet networks. So end-to-end scheduling seems to be possible. Just to show you, these are some of the initial results. So you can split the time in multiple slices. It's a kind of airtime slices. And within the slices, you can, this is how we do it today. I'm not saying this is the best, but just showing there are some new capabilities that you can exploit to build time-sensitive networks and to also have very accurate scheduling at the wireless level, extending Ethernet. This is, I hope this is working. There are 2 videos here. Where we did some end-to-end experiments, and on top you can see the experiment done with off-the-shelf devices. This is done with a prototyping platform, and there is one yellow flow. No, the green flow is a time-sensitive flow, and the yellow flow is a non-time-sensitive flow. So you see when the yellow non-time-sensitive flow is switched on, in both cases you keep lower latency for the time-sensitive devices, but still on off-the-shelf today, it's order 50 milliseconds. I'm not sure if it's visible. And here it's in the order of milliseconds, sorry, for the end-to-end. But just to show that time-sensitive is possible and can be further boosted. Here you can see some more detailed measurements where you can see by innovating on top of open platforms, you can achieve big improvements in terms of guaranteed latency. Just to show here end-to-end latency, 99 percentile. It's in a multi-hop wireless network. It's only a few milliseconds. Okay, it's we can still do better, but at least it's way better than what you can do today with off-the-shelf devices, which is in the order on average of 60 milliseconds. Fine. But then this is about scheduling. Of course, you can all do that, but how do you know that you are achieving your targets? So you need the verification. Also here, we did some wireless extensions, and we were inspired by what is happening in data centers. And although everybody is claiming for the separation of data plane and control plane, you have to realize that in many systems, in particular in the wireless interface, the control, signaling, data information comes together, and you have limited spectrum to do that. So what we are using is in-band telemetry. So actually what we do, we have telemetry data, monitoring data, and we piggyback it to the data packet. And in this way, end-to-end, you can add more information, inject more information. Does not need to happen in all packets. You can decide, it's a matter of scheduling, but in this way, and that's the nice thing, you can collect all kind of characteristics. It could be as well node characteristics, could be link characteristics, could be flow, end-to-end flow characteristics. For example, we can piggyback timestamp our hardware timestamp information, and we can very accurately monitor end-to-end latency. So this is a way for verification. And just to show you some examples, we can also, in between nodes, for example, in an access point, we could monitor the queue filling and the queue occupation. We could even measure processes, delays of processing delay in the node between the network and the application. What else? We can monitor the number of retransmissions, end-to-end delay, RRSI, whatever is exposable, whatever parameter you can extract from the system, you can monitor it, inject it, piggyback it to the regular data packets. And based on this information, based on the insights you get, you can do a flexible configuration. And in this way, you can keep the network within the requested quality of service requirements. And just another example, and I won't go too much into detail, we also used our telemetry to monitor, for example, the congestion window in a TCP end-to-end TCP connection. And then you can indeed see that there is a correlation between the monitoring packet loss or monitoring via the in-network telemetry and the congestion window. So by monitoring queue occupation, you can actually use different algorithms, and we have exploited that. And then you can see that you actually can improve end-to-end communication. Maybe you don't need TCP anymore. Maybe you can use other metrics. Just to come to my last slide, because I think this is perhaps the most important one for triggering further discussions. It is very important, although I agree that we have to push limits and go for other technologies and new technologies and all that. But something we are overlooking is we need good timekeeping technology. You do not necessarily need atomic clocks for that, but timing, the time, global time awareness is so important if you want to deliver strict guarantees. And here you can see a picture, I think it's quite recent, something that was announced, I think this week or last week by Facebook. They also did some effort on a time sharing card. It could use atomic clock, but it could use any other clock reference. But apparently it seems that this is indeed a topic which is gaining more attention. Another thing is that, of course, in order to offer services, the application has some requirements, but how does the network know? And I think here maybe the semantics and the semantic communication comes into play. We need a more expressive and technology agnostic interface, because applications should not be aware which technologies are below or are taking care of the communication. And in this way, application can actually communicate its desires to the network, but also on the other hand, the application should also know what are the limitations of the network. But this, I think, is lacking today. There is still a lot, there are many good technology, but the way, or you have to do it with kind of setting, fixed configuration, fixed agreements. Next thing is measurability. Is very important. Not sufficient monitoring capabilities are available. Radio technology today have a lot of information, but it's not exposed or it's not used in an efficient way. Also here, I think the intelligence can come in. I called it advanced analytics, but I think machine learning techniques and AI can be very helpful here. But, and I think this is also in line, we should try to get maximal insight with minimum overhead, because please also take into account efficiency of system. Of course, you can monitor everything, bring it to some cloud that can do sophisticated processing and analysis, but this will induce really a lot of extra information, even much more than the information that matters for your application. Also, in terms of scheduling, things should be much more autonomous than before. It's not a matter, wireless environments are changing rapidly, traffic demands are changing rapidly. Forget about these fixed SLAs and fixed configuration. This is not working anymore. Seems quite obvious, but it's still not available today. And I think we also have to think about KPIs. What are the KPIs that matter? I think the KPIs should be truly end-to-end. And this is not only for performance, for latency, end-to-end latency matters. And latency over one link or over just the wireless doesn't mean anything. It's only the end-to-end latency that matters. And this is not sufficiently addressed today. But don't only look at performance, also look at efficiency. And in order to go there, I think we need some more openness. Openness at all levels. It could be in the open hardware, open software, over interfaces, over algorithms, standards, whatever. We need more openness for boosting innovation. We also need more end-to-end validation. To my opinion, we are working too much in silos. We are looking all in our own silos. We have to come out of our comfort zone. It does not help to just increase capacity. We have to look more from an end-to-end aspect. If we want to deliver end-to-end services, we have to look more. We have to look at co-design, things like that. So it's not just about one specific topic. We also have to look at the full picture and solve the real problems. And I think that's the last thing. And this you can only do by looking at more multidisciplinary research. The co-design and multidisciplinary research. And maybe it doesn't look so exciting what I presented. It's not like a vision, but I think we have to go further than just looking at the next technology that can push the limits. There is much more than that. So I will end here. Thank you very much.
Yes, thank you very much. Actually, I found this talk very visionary, and what I like also very much about the results, the impressive results that you've shown, that often openness and performance seems to be a contradiction. So those platforms which are open do not perform very well. And you have shown with your results that the open platform can be very performant and even better than commercial platforms. And I think that's a good basis for developing future communication capabilities. So thanks very much. And I see also that there were some questions in the Q&A which addresses exactly your point on the global timing of the systems. And we will take this question later on.
I will look at the questions and
thank you very much,
for
your talk, and then we discuss later in more detail. And therefore, I would like to forward now the screen to Harris to provide the third talk. I've seen him just a minute ago. I think he should be still online. I think he was online, just as I saw his video. Haris?
I am
Yeah.
online. I'm trying to figure out where am I on the screens. So I'm sorry.
Okay, great. Yeah. So you
so
just,
let me just try to. Yeah, I have this one. Share. Share. Just 1 second, please. Share.
maybe you
yes.
have you started already the presentation mode of PowerPoint? Yeah.
Yeah, I think it should be. Do you see the?
Yes, now we see it, but we see it in the
yeah.
the reference.
I have to change here. Just 1 second.
Yes, now
it should be fine. Okay.
Great, thanks.
Okay, so thank you very much, Christian, for the invitation, for organizing all of this, and I think it was definitely a big effort. So I'm going to talk about a vision that I have for the 6G wireless communication or design of the physical layer, and how the physical layer should react to this new requirements. And let me just switch the slides. I have to do like this. So before I start with any kind of technology and the discussions about that, let me just give you an example of what do we want to expect, or what do we expect at all in the visions of the next generation wireless communication system. So imagine that you are feeling sick, you are coming home, or you are at home. The wireless network is able or is capable to detect, to understand that you are not well. It is starting a cyber physical interface that is starting to communicate with you. The holographic doctor is popping up and starting to ask you to diagnose to see the situation of the state of your health. And after a few minutes or dozens of minutes, either the recipe comes, it's ordered through the local pharmacy, and your medication is delivered to your home, or in the even a little bit more serious situation, the ambulance is already directly called from the hospital, and they come to your home and take you to hospital for some more serious treatments. So this is the vision of a future that I have, where the wireless networks are going to play the role. Now, what kind of technologies that they will be to provide and to secure such a services, that is another discussion. But what I want to have here is definitely, I think what we have to understand, it's everything is about us. Everything is about us as a customers, as a humans, and no matter what kind of technologies we design to support us, to serve us, they will be always tailored to our particular needs, and that is the future that I see in wireless communications. So if we just now try to translate very fast, the example that I gave into a few lines of requirements and the building blocks, what we need for that. This is what you get in a nutshell. So you have a edge cloud on one side, and you have a local cloud. So this is for critical computing, local cloud for critical computing around the user and around the user devices, to cope with those requirements and restraints that we have on the latency and the computing power. And then if you need more, then you have to push everything to the cloud. And that is something that was mentioned by Mehdi in the beginning, that we are facing problems with the computational efforts with AI. But then we are facing with this round trip latency that we have, and that is something that we cannot avoid. So in a nutshell, we need a flexible computing designs. Then this is on the computing side. And then what is about the network? So if we take an example of our home where we are, then we have to face the situation that we have to distribute our processing across different devices, because we just don't have enough power and enough time to produce such a precise measurements and compute them in the right way. Then we have to control the network, or we have to control all the devices at the same time, and we have to provide in order to provide the services. So that requires additional APIs or the standardization bodies to be included, and that leads us to the autonomous network operation. That is something that has been with us for the many years. It was called self-organized networks, automation, advanced automation, autonomous networks, etc. In a nutshell, what we are dealing with is a small transformation from centralized toward a distributed processing, communication, or computing, learning, and sensing. And this is what my talk is about. My talk is about this transformation and the requirements of in order to hit these kind of requirements. So now, what do we need and what do we have on our disposal for this flexible connectivity that we want to achieve, where we're connecting the intelligence through from different devices through learning in either fast learning from the limited resources, computing resources, or let's call them unlimited in this case, or the edge computing facility. So we are talking about distributed connectivity. That is our driver. We're talking about communication sensing that is going to be ingrained into the infrastructure itself, communication infrastructure itself, and computing communication. So computing needs to be a part of the communication infrastructure. And we just cannot say that, okay, we have a wireless infrastructure, we have a number of nodes, and then we are going to offload computing to the edge cloud. This was this is something that was quite accepted, and maybe even still acceptable, a term that we are going to just do everything in the cloud. This just doesn't work like that. It will not work like that now. So where we are now today with computing is or with the network itself. So we have, if we take a look at the reliability and the latency coordinating system, then we see that we have three types of services. We have ultra reliable communication, ultra reliable and low latency communication, and we have a low latency communication. So our 5G network, when we deploy it, it's dedicated. It's dedicated either to one of these three. Yeah? So this is what we have today, and this is how we deal with it today. This is fine, and we are happy with it. But where we want to go? We want to go into the space, into the area where we are going to switch simultaneously across different requirements. Now, in this case, I don't say that LLC or LLC and URC are going to be these requirements for 6G. I'm just saying that these are the ones that we feel now as the most attractive one, but definitely maybe there will be multiple of them, even more. But whatever, as many there are, our goal with the Beyond 5G is that we move the working point of our system simultaneously across all three of them with the same network, so that our network becomes flexible. So we have a flexible infrastructure that is going to be autonomous in order to adapt itself to the customer needs and to the needs of the services that are coming in that sense. Yeah. So now what we are starting to face with. You are starting to face with a connectivity transformation. We are transforming our connectivity infrastructure to be scalable in the real time, and to have AI embedded on the node itself. So we are talking about a distributed learning for environment-specific applications. So this is our main goal. This is the goal where we want to go, what we want to reach. But what is the challenge within this goal that we have? So we have to make sure that we devise a practically effective embedded learning or embedded intelligence per devices. So we have to make sure that we are enabling planning, learning, and searching of connectivity mechanisms, so that the network itself is becoming a densifiable and re-expandable in the same sense. So that when we need more or less, we are able to do that on the fly. So this is what the change of our infrastructure should look like and how it should be. Now, if we are going to reach it for 6G or not, I don't know, but this is a general idea behind this transformation. And now now what we have, when we are talking about communication, we're talking about sensing, we're talking about computing. So we have the connectivity design that is going to follow certain architecture of the latency, reliability, deployment, mobility, something that Ingrid was just talking about as well. This is something that will not change. It will always be with us. The reliability, latency, these are the KPIs that are coming all over and over. Then ambient intelligence in different flavors, either at our home, at our offices, at factories or verticals. So this is again this ambient intelligence. It needs to be integrated with the infrastructure, with the connectivity design itself, in order to adjust the infrastructure in a way that requires a particular location, activity, or the emotion of the user. And then at the end, where we are coming in on the low cost and low computations. We are not having the privilege of edge computing everywhere. We don't have a privileges of huge servers, GPUs, etc. So from that perspective, we are looking into the AI or the machine learning that can be integrated, that can be jointly integrated with the signal processing. So we are talking about the merger of signal processing, traditional signal processing, and new and advanced machine learning techniques. So then what kind of technology components do we see there? So first of all, we are looking into the soft radio infrastructures. So we are looking into the nodes that can be refreshed, that can be the change their structure, it can change their the communication protocols on the fly when needed, when required. So this is what the future will bring us in that context. Then we are talking about the distributed communications. So we are talking about more and more about further densification, because when you look at the communication systems, the true capacity was coming always in 90% of its volume was coming through densification of the networks, not through enhancements of the physical layer, RRC layers of networking and so forth. No, those are the things that were playing the fine tunes, but the major major improvements in capacity of the networks were coming from densification of the networks. So we are talking about the further densifications, and there definitely distributed communications will have to play the role. Here we are coming again to the radio resource management. It also has to follow the same structure as a distributed communication systems. Immersive sensing and communications. This is again integration with a current distributed network, distributed connectivity that is going to play the role to communicate with the customer, to be able to change the infrastructure based on the customer needs and customer requirements. And at the end, we are coming to the point of the communication computing. So we are either talking about real-time or embedded AI. In the real-time, we are talking about some controllers that are going to be run in the cloud, that are going to have a capacity to run the systems on the fly. However, that is not what we may need for the real-time services. We are talking about then embedded AI to support such a learning capacities. Yeah. Then last two slides. The requirements of the 6G in the perspective of what I was talking about are online radio operation in real time, all the time. So you are talking about the real-time learning at the speed of targeted radio application to radio interface. And then we are talking about sub-millisecond, not sub-second actually, sub-millisecond distributed communications. And if we look at that as a summary, then it is very questionable if we can talk about AI as a design parameter of the 6G. No, I think the customer needs and what we are expecting from the customers to happen will give the flavor to our 6G design. Distributed communications in the sense of further densification and learning and computing to support it. And from there, we are talking about the embedded AI, as a fusion of the traditional signal processing and AI or machine learning techniques and the real-time AI that is going to be facilitated by some edge computing facilities. So that's it. Thank you very much, and I hope that you have enjoyed the presentation.
Yes, thank you very much, Haris, for this very inspiring presentation. I was the idea or the notion of soft radio communications may also have an impact on the way we standardize the systems. Maybe there's a different need for standardization because right now we are standardizing the complete radio interface in very much detail. With a soft radio approach, it might become a different story. But maybe we can address this later on in the Q&A session. But thanks a lot for your talk. And let's move on to the next speaker, Thomas Kaiser. Actually, some note, there was a typo on my slide previously. There's not an hour intermission. We continue, of course, with the talks now. And I would like to invite Thomas to talk about terahertz communications and sensing.
Thank you, Christian, for the invitation and for organizing this rocket session. Can you see my slides? Is that okay?
Yes, we see the but still in the presentation mode.
Okay, so, then I switch
in this,
to the.
It's not full screen yet.
Now it's full screen, right?
Yes, now it's full screen.
Okay. Then let me start. So what you see there is Christian already introduced the project 6G, where most of us, Haris, Christian, and me, we are part of. And I will talk today about terahertz for 6G. And there's another project which started in 2017, and that is called Marie. And what I will give you now is an overview what happened in principle in both projects and what are the key trends in terahertz for 6G. And it's a composition of these both projects. So let me briefly introduce Marie. That the title of Marie is Mobile Material Characterization by Electromagnetic Sensing. So it's not related directly to communication. It is different material characterization. It is a large-scale project with 27 scientists and 31 PhD candidates. Main partners are the local university here, Bochum and Duisburg-Essen, and the smaller partners with most of the PIs. And smaller partners are Darmstadt, Dresden, Wuppertal, and 2 Fraunhofer institutes. We started with that in 1st January 2017. We are currently in the second phase, and that runs until end of 2024. And now comes the most important point. The frequency range, what we address there is 250 gigahertz to 5 terahertz. So it's not the typical range what you consider in communication with terahertz up to 300 gigahertz. It's above. And the reason why it's above, because communication is not in the focus of the project. But, and that is what we see more and more, in future 6G, different, let's say, technologies will merge to each other. And that is the reason why I would like to include Marie also in terms of the 6G terahertz trends. So what Christian put on the website is this key question here, or key questions. Which 6G key trends are target-oriented in order to guarantee industry-oriented development and research, as well as a basis for later commercial exploitation under the label 6G made in NRW. So NRW is our area here, and that is what I would like to address at the end. And in the meantime, I will address the 6G key trends based on terahertz from, you can say, from the outcome of the Marie project and from the strategy for the 6G project we started a few weeks ago. So let me start with a very simple slide. What you see here is atmospheric attenuation over frequency. You will see there from 0 to 0 gigahertz to 1000 terahertz. You see the blue and the red curve for different environment conditions. So the red curve is for dry air, and the blue curve is for normal air, so with some water content. And on the x-axis, you see the specific attenuation in dB per kilometer. And the reason why I put that slide in the beginning, this slide you see pretty often when we talk about terahertz, is that it looks a bit ugly. You see the spikes typically come from an H2O. And these spikes, of course, hinder to go for long-range communication, for instance. But actually, it's not so severe. So I put here one green line. I hope you can see that. And what I assume is I could accept an additional attenuation by atmosphere of, let's say, 10 dB. And if I do that, and I go indoor approaches for communication, for instance, up to a range of 10 meters, yeah, then all the spectrum, almost all of the spectrum is available to me, except of this range here around 500 to 600 gigahertz and a bit around 700 to 800 gigahertz. So in principle, there is a lot of bandwidth available when I'm focusing on, maybe better to say not indoor, but in room, because at these frequencies, nothing is propagating out of a room if the room is closed. So, but you can serve rooms with a size of 10 meters, and then you have spectrum availability of several hundreds of gigahertz even. And if you do that outdoor and also accept that, let's say you go for 10 dB attenuation, then not all of them, you see here some additional peaks in blue. So the auto is the black line, then you see some additional peaks in blue, which are not able, let's say, which is higher than the 10 dB, but also there is plenty of spectrum available. So the atmospheric attenuation, I would say in typical terahertz applications, it doesn't play a major role. So the next one, what plays a major role is of course technology. And what you see here on that slide is different, let's say, trends for different types of semiconductors as a function of frequency and how much power in principle you can transmit with a power amplifier. And you see the typical CMOS curve, silicium, germanium, and indium phosphide. And what you see, the yellow curve is indium phosphide, and you see it goes already up to 300 gigahertz, so 100, 200, 300. And when you go from indium phosphide, from this point at 300 gigahertz to the left, then what you see is you are a bit above 20 dBm. So you can transmit at 300 gigahertz with around 20 dBm. Yeah, and if we have 20 dBm, and we would like to go, for instance, at 300 gigahertz, we would like to go for 100-meter range, then with just 25 gigahertz bandwidth, we can go for 100 gigabit per second. And of course, you can scale it up and down, yeah, depending on how much bandwidth you spend, yeah, and whether you go for 10 meter or 100 meter. But what you see here is there are materials available, which semiconductor materials, which are able, even today, because some of these bars below the indium phosphide curves are close to that, even today, there is no big, let's say, barrier which would hinder terahertz communication or terahertz applications to be realized. So that was about transmit power. And now what about regulation? Regulation, even 2 years ago, FCC opens, you see that there 95 terahertz, gigahertz to 3 terahertz spectrum for 6G, 7G, or whatever is next. Yeah, that is what they told us for experimental licenses. So we can do it. Yeah, so it's not the way that there is anything which hinders us to make products. Yeah? Even nowadays, of course, it will take years, as Christian indicated, probably additional 10 years until we have the products, but then for additional 20 years. Yeah. Okay, so first trend, that is terahertz trend, that is very clear. That is what most people talk about. That is, of course, just get data rate up. What we will try in the 6GEM proposal in the project, we would like to go up to 1 terabit per second. And the challenge there is, of course, that is what I mentioned before, is low TX power. That means low coverage, yeah, meaning 10 meter, 100 meter maybe, but not for 1 terabit probably. And the solution, what you need there is not only this transmit power. What I didn't say on the previous slide, I assume always that I have a lot of gain due to beams. Yeah, so this beam, you see the sketch on the right-hand side. It is a directivity of 26 dBi in the main direction. Yeah, and that is a 24 by 24 antenna element array operating at 300 gigahertz, which is already, let's say, under development. And if you have such beams, then of course you severely suppress the multipass. And an open question still is whether the suppression could be so good that you do not need an equalizer. And with these high data rates, I think equalizer to build might be the real challenge behind that. So that is first terahertz trend. Second terahertz trend is simply radar systems. Today you have automotive car industry with radar systems operating between 76 and 81 gigahertz. That is today. In the future, for instance, it could be 275 to 325 gigahertz. So then you do not have 4 or 5 gigahertz of bandwidth. You may even have 10 times of that. So you have a very accurate range resolution. But also you have a very nice lateral resolution, because if you go up with frequencies, then antennas get smaller. So antenna separation gets smaller. So on the same surface, you can afford much more antennas. And then you have a much better lateral resolution also. And you can use that for all these autonomous topics like cars, trucks, ships, trains. We do that in the 6G proposal. We have Aldenhofen Testing Center. That is, as far as I know, Germany's largest autonomous testing center. We have here a very nice other test bed. That is our harbor here in Duisburg, which is the world's largest inland harbor. So also a lot of opportunities to go for autonomous trains, for instance. And all these things, what you do with your gesture, with terahertz, of course, you have much more resolutions there. So another terahertz trend, that is coming from our project Marie. In principle, that is terahertz indoor imaging. So what we mean with that is the following. You probably all sit now in a room. You can see the room with your eyes. You can build up an optical picture of that room with colors. But what you do not know is what kind of materials do you have? Is it concrete? Is it plastic? Is it paper? Is it whatsoever? And when you do terahertz spectroscopy and you fly around, then in principle you can assign to this room also a material map. And that is the vision of our Marie project, to assign a material map. And you have an example, a colorful example in the picture there on the right-hand side. When a fireman enters, for instance, a room and he knows the material map about it, and even if the room is totally smoky, he can watch through with a drone and he can build up all these, let's say, type of objects which are critical, and he can then, let's say, distinguish and not, how is it called? You would like to kill the fire at those places where it's really critical. So that is third terahertz trend where we are heavily working on, and of course that goes to very high frequencies. Yeah. And even there we will go for mobile devices. I will discuss that later on. Yeah. So up to 5 terahertz. And of course not with electronics, we have to go for photonics or maybe even a mixture. Another thing, what you need in order to do this terahertz imaging with sufficient accuracy, you need an indoor localization system where you know how the drone flies, and accurately you need the accurate trajectory of it. What accuracy means is, in principle, you need sub-millimeter accuracy indoor. Today, what you have is, ultra wideband, and in ultra wideband you have a few gigahertz of bandwidth, and typically you can go, let's say, 10 centimeter resolution, maybe even less when you exploit the full ultra wideband range of 7 gigahertz and you have reasonable SNR. But with terahertz, you can, let's say, go up with an order of magnitude. And you see on the right-hand side one curve, which shows the CDF of the localization error. And even for 10 gigahertz of bandwidth, I can go in the range of sub-millimeter accuracy. So in principle, we can do that. In NRW, we'll work in the Marie project on that. So then comes another aspect, environmental monitoring, what you can also do with terahertz. There is already a drone available. You see that in the picture there from a very innovative company. It's called Beckman Technologies, coming from the US. And with that drone, they measure, for instance, the air quality, the pollution, and it's just flying around and has the terahertz spectroscopy device on board. This spectroscopy device is still rather heavy. I remember it weighs around 3 to 5 kilograms. Yeah, what you see on the picture there. And in principle, you can also miniaturize it further. And you do with that, air quality control, gas sensing, agriculture monitoring. So let's say topics which are not very common in 5G or in 4G or in 3G. Yeah. But in 6G, you can merge in principle all that what I'm showing here as trends. The last trend, and that is where we do not yet have a large-scale project for, so we are not working there with many people on that, was just a few projects. And that is, of course, what about terahertz and medical? There are approaches to do a better skin cancer diagnosis. So you radiate terahertz into an area of your skin where you assume that there is skin cancer, and terahertz propagates into the skin, and then it reflects, and then we hopefully can give the doctor better advices whether this type of cancer is good or bad. Another topic is blood sugar analysis. Honestly, what I believe is that terahertz is here not the right tool, but we do not yet know. The lower the frequency, the better you can go into the skin. So maybe millimeter wave are better, but that is still under discussion. Another topic could be dehydration measurement. So when you are an old person and you don't like to drink anymore that much, then your watch could inform you your water content in your body is too low, you have to drink, and that is what of course you can do with terahertz. So there are many unexplored areas regarding exporting terahertz for medical, and that is where we currently started to prepare a large-scale proposal also for. So these two slides, I think some of you already know. We have colleagues here from the 6G flagship program, so I won't go into detail, but these are also applications for terahertz which are closely related to that what I've shown, or also different from that. That comes from the 6G flagship program, and then there's the Hexa project, HexaX project, where you also have many different. You see massive twinning, that was also wording which is used today, or the consumer robots which are collaborative by nature with the people, yeah. And these are other areas where also terahertz could of course play a role. There is certain overlap. These terahertz trends, what I have shown, are the one which I believe that we understand better and better. We do not understand them well yet, but we understand better and better because we are working on that. Yeah. So what is also, I'm coming to the last slides, what of course is also very important is, although terahertz radiation is non-ionizing and the transmit power is rather low, but we have there a lot of antenna gain. So we are talking about 20 dBi and maybe even more. And if we put that device maybe close, I do not know, close to your eyes, close to your skin, yeah, and it's a mobile device, so you can do with it whatever you would like to do, yeah. And then of course we have to investigate the impact of that. And simply speaking, what we are working on is a ray tracer for terahertz. That is what you see on the left-hand side. And on the right-hand side, one of our colleagues here are going deep into the details of the human skin in order to fully understand what is the impact of this radiation, and also what is the impact on certain applications. So to put two sentences above the full story, so future 6G terahertz products, they should be compact, they should be of course energy efficient, and they should be mobile. And when you take a look today what is available, you have this bulky terahertz measurement devices. And what I remember pretty well when we started, for instance, with 4G, that was around, when was it, 20, not completely 20 years ago, but 18, 90 years ago, there were also this bulky measurement equipment, yeah, and at the end you make a device out of it. And exactly here it's also the same. So we would like to make mobile, compact, energy efficient devices, and that is the task of these both big projects. So in Christian's slides, or in Christian's question, there was 6G made in NRW. So I'm a local person here, so I'm highly interested to push us forward also in 6G, and how to do that. And I think the answer is very simple. We are in such early stage in development, and typically the big companies, some of them already start to contribute there, but this is a great chance for startups. Yeah, and that is what I would like to motivate the full auditorium. Think about that, whether that could be a potential also for you. And we have in Marie's first phase, that was from 2017 to 2020, we already launched 3 startups, and I believe also in 6GEM and Marie more will follow. Yeah, and can only encourage you to think about that and maybe to become part of such a team. Okay, so that's part of my talk. Thank you.
So thank you very much, Thomas, for this inspiring talk, not only for North Rhine-Westphalia, but also beyond. And it also shows that basically the ideas around 6G are more than communications, much more than communications, application related, sensing related. And maybe this is now the time to move to the Q&A session. And maybe from that view that 6G seems to be much more than communications, I would like to take up the question, what role standardization will take in 6G, because traditionally we have seen that all the generations are being specified mainly through 3GPP, but on some of the slides from Harris and also from Ingrid, we have seen also Wi-Fi being mentioned. So, and when we go into this, the idea of semantic communications, is that something we perceive that traditional standardization will move this forward, or is there other mechanisms to convey these ideas? Are there anybody wants to start to comment on this? What's the role of standardization in the future?
Well, I can start maybe, because I always get this question actually when I present this vision. People somehow rush to the standardization, but I think what I tell them always, no, this is a scientific, this is a mathematical problem. We need to understand, we need to define what semantic information means. We need to define new metrics to evaluate that the communication actually is under this level, B level C. Today we use mutual information, right, between X and Y, arguably to calculate mutual information, which is a correlation-based metric. No, we need kind of new metrics before we even start to think about standardization. But of course, under system one, semantic communication, as I was saying, arguably today, people are doing semantic communication because in video streaming, you can argue they are doing it actually, right? This codecs of MPEG 2.3, right? Semantic is there because, this is how you have a video, you extract you compress the video, right? And then you transmit it over the air. This is already done today, but we need the other level, which is much harder, right? And then of course, yeah, because this is, if it works, if you just think about or entertain the idea of new protocols for robots, I think it's not gonna be done within the next 5, 10 years. I don't know, right? But to me, just to maybe finish here, I think 5G should have been about, or maybe the current 6G or 5.5G should be, yes, about integration. Yes, because yeah, people have been working in silos and stuff, but the revolution should be scientific, not business driven, not standardization driven. Okay, I hope I'm clear here. We need to go back to school. Right. Okay, great. So this is much too early, and we are in the early phase to already think about who will standardize it. Yes, please, Ingrid.
Because I also have my feeling you have different approaches for standardization, and sometimes when you compare, for example, 3GPP versus IETF, I think radio communication could also benefit from the principles used in IETF. If you want to get something standardized in IETF, you first have to prove your concept. You have to build several independent implementations. You have to prove that it is interoperable and then it is accepted and adopted as a standard. And sometimes I have the impression that we are doing it the other way around. We have idea, we want to patent it, we push it in the standardization. Maybe exaggeration, but we don't care at first sight if the performance is better or not, as long as we can push it in standard and hope that everyone will adopt it because it is a standardized document. And I feel that it should be more driven by real innovation and proven concepts rather than just pushing something on paper and then see where it gets. Maybe I'm a bit too extreme, but but I think we are a bit over standardizing, and it limits also innovation, because there are so many specifications in the standard, even if the specification, not all specifications lead to adoption. And sometimes it is a showstopper for innovation, because we are restricted by many standards. While if you can break out of the standard, you could push for better concepts and then see how you can best standardize. But okay, maybe this is too oriented opinion. But we see sometimes that we are really blocked and hindered by standardization, while we see concepts that are more simple, more dealing with the real problems than what is currently presented in the standard. But okay.
So maybe the soft radio promoted by, mentioned by Harris would be a solution.
Sorry, I was muted. So, well, I honestly, I will tell you honestly, I don't know. I hope so, but I have a few comments to give to my dear colleague and friend Mehdi, Ingrid as well, and the audience. So yes, indeed, it is. We would all like that it goes over the revolution, that we bring new things. That is our job as academics. But I think the reality is a little bit different. Reality. And the standardization and industry is driven by businesses, is driven by the revenues, and there we don't talk about, unfortunately, about revolution. We talk about evolution.
Make money.
Money.
Yeah. Well, I mean,
very simple.
Well, let me just try to be honest at the moment, right? So from that side, standardization is expected to not to innovate. We are expected to innovate, and they are expected to bring that to the market. That never happens when we do it or when they do it. It always happens after a number of years of careful investigation, testing of the different technologies, bringing them and actually looking who has the IPR here and there, and then squeezing that everywhere, that everyone has the benefit out of it. So, but that doesn't mean that we are in collision, yeah, right? So I think the standardization will go as it is. When you say 6G, it is about cellular, it is about 3GPP, it's not about IEEE. IEEE follows very well. They do follow with new technologies, new data rates, etc. But when you say 6G, my thoughts are on the 3GPP, and this is going to happen like that, I'm sure, since I'm in this business. So, question about what revolution will bring. Revolution will bring what we can dream of, right? I mean, we are talking about semantics, we're talking about programmable networks, flying drones, all of these things. This is far away from the industrialization, but if we don't do it, then it's definitely not going to happen. So I think it should come to these agendas, to these discussions, and then when the industry will pick it up, I don't know, but I hope it will happen. But we need to ripen it for them. That's the opinion.
So first, investigate and show the performance, and then hope that the business people would want to pursue it in the future. Okay, so Thomas, one idea on standards, or should we move to some questions from the Q&A?
There could be such a variety of products, which for instance, just to give you an example, the pencil where you can hopefully detect cancer with, is of course not related to 3GPP. Yeah, it's just a product which you can bring on the market, and if it works, everybody would be very happy. Yeah, and it may follow some other standards, but not the one coming from cellular communication. Yeah, but it's based on a technology which will be also used for cellular communication. Yeah, so I think there will be a lot of things which we never saw before yet. And then it's hard to say what kind of standard it will fulfill and how it will progress. I remember a slide from Roda and Schwarz, and they predict release 22 or 23 in the year 2030. Yeah, something like that. Yeah, that is quite ambitious. Yeah, to say it will come. Yeah.
Okay, but probably that's the most important point, that not everything needs to be standardized, and that probably the focus of the standardization might be adapted throughout the evolution towards 6G. So I'll take a look at the Q&A section, and we have already had some questions which have been answered. So I take up those questions which have not been answered yet. So the first question from Peter Decker, basically, hello Peter, he's a former colleague of mine. He asked about the role of MNOs, manufacturer service providers, with the more deep integration of communication and data. I had also the idea that this idea of semantic communications also involves that much more knowledge about what is actually happening. It's not a bit pipe anymore. It's there's some more knowledge involved, and how does it change the role of the players?
So what I think everybody got the intuition that the vision is very simple, but the difficulty is how do you make it happen? So in fact, to directly answer the question, if people are interested in what a disruptor in the ecosystem is, I recommend you to check Rakuten. I think everybody knows what Rakuten is. Rakuten is funded by a millionaire in Japan. I think Hadis may know better than me. And actually their role is very simple. They come up with this autonomous network idea, which is very related to what I'm talking about. Essentially, they talk about a hierarchy of multiple control loops, which are sensing and trying to build a kind of an image or a map of the environment and act upon it, everything from data. They also talk about knowledge structure. They talk about generalization from one environment to another. So that's one application, let's say, you can call it of Vision X. So it's happening. Of course, now how do you standardize this interfaces? It has to be, I mean, this abstract interface, it has to be exposed, like Ingrid was saying. This is a very important part of this, right? What the application needs, what are the requirements, all these of course have to happen, but my role is I'm trying to go through this through a more theoretically grounded approach, because then it will solve all the other problems.
And do you see an impact on data privacy? That's also one.
So something was mentioned in chat. Yeah, I haven't mentioned. So my previous life or my current life, maybe, I work a lot on federated learning. So federated learning is exactly what Haris was trying to say. You don't want to ship the data to the cloud for privacy issues, but for us, we don't care. Perhaps we care maybe about bandwidth. So depending where you are in the Pareto boundary, so you need to ensure privacy. So you could use federated learning for that. There are many other techniques that outperform federated learning. Yes. Privacy has to be there as a kind of a clean. I mean, from the get-go, not as an afterthought. This was one of the novelties of 6G requirement. To some extent, I think it's just expected. So yeah, privacy is number one. Then sustainability and resiliency. So resiliency bothers me a bit because it's a buzzword we are forced to put because we get funded, right? But we need to break it down in terms of what we really mean by that. Resiliency in what? I mean, cyber attacks. In machine learning aspect, because it's there, right? How do you generalize to a new domain where you have zero data? How can you operate, right? Essentially the long tail problem. That's what resiliency means to me as well, right?
Yeah, thanks. Another question is related to terahertz frequency, and it's also related to the range of terahertz. So is it a correct assumption that the terahertz application area is mainly focused on indoor environments, or that's?
I would even say not on indoor, on in-room.
In-room.
So to put it, let's say when you today have a flat or a house, then you may have 1 or 2 Wi-Fi access points operating at 2.4 or 5 gigahertz range. Yeah, and when you go for terahertz, of course, you cannot penetrate through material. And that means per room, what you have, you need an own terahertz Wi-Fi access point, and they might be connected by an optical fiber if you drill a hole through the wall. Yeah, so that could be a solution for that. Yeah, and that is, of course, you reduce range, indoor range. And outdoor, of course, you can also do that outdoor. That is the same discussion like with millimeter wave.
Yeah, actually, in the session we had on Monday, it was focusing on security aspects of 5G, and there was also a discussion on millimeter wave, and there millimeter wave was also promoted as a tool for higher security because it's limited to the room, so you can communicate safely inside the room and do not worry about the outside. So that's maybe a good way of trading these characteristics. Yeah.
You have to find the beams. That is the challenge. Yeah. And if you're not in the beam, then you cannot listen to them. Yeah.
There can be another issue for privacy. You can have the data privacy, but there is more than the data, because now you have this joint communication and sensing, which is another risk, because even if you cannot understand the data, you can monitor the behavior, so track people, which is another issue, which is getting more and more dangerous, because it's also one of the key topics that is promoted in 6G, but I think it also has some privacy issues. So sometimes calling, you can do sensing, which is great, but maybe you also have to foresee anti-sensing. What if I, with my device, I don't want somebody else to detect radar or to track my location? We do some work because we have open hardware. We can do something where you can influence the channel state and mislead. You can also do anti-sensing. You can always use and misuse technologies. Something we have to be aware of.
Yeah. There's one question in context to this limited range, is if 6G is replacing Wi-Fi. Maybe it's a general question. If there will, of course, there will be probably a Wi-Fi 7 and 6G. Will it be separate technologies, or will it converge? Any views on that?
I don't like when I hear this question, because does it mean Wi-Fi is not part of the discussion? I mean, for us, at least academics, this is irrelevant question, because no, Wi-Fi has to be there.
So
has been said that the third generation would replace Wi-Fi. It has been said with the real data, the internet, 4G, then 5G, and now 6G. I think both will survive and both have a role, and it's not the one or the other. I think there is always be a complementary usage. I don't believe that one or the other will disappear. It's not a matter of, and that's perhaps something that is a pity, and which is also somehow putting some limitations on innovation, because people always think 5G, 6G, 7G, whatever, it has to focus on mobile networks and it should be cellular. I do not agree. Personally, I do not agree. I don't care which is the underlying technology. If you look today at the standard of Wi-Fi and LTE and 5G, it's not so different. I don't think that's the key mechanism. Of course, the spectrum. Why wouldn't you use Wi-Fi technology in the 3.5 gigahertz band? You would have the same or maybe better and probably a cheaper network than a 5G network. So I think
there's probably more branding issue.
I think the functionality matters. It's not so much if you call it Wi-Fi or if you call it cellular. Look at the features, time sensitive. I don't care. We prototyped it with Wi-Fi. I don't care if it is Wi-Fi, but Wi-Fi was an open platform. If I would have open platform with LTE, I would be happy to put it on LTE. But I think the functionality and the feature is more important than the name of the technology. Okay.
Yeah, I fully agree. Actually, I came across recently in an internal discussion, we discussed the differences between Open RAN and ORAN. So, yeah, because ORAN is probably the standard way of doing it, the alliance way of doing it, and Open RAN maybe more broader understanding of a radio access.
Discussing too much about the package, while we should focus on the content, because the package for me is the standardization that comes later. But first you need the content, the functionality. We have great architecture now that can do orchestration, composition of functions, micro services, whatsoever. But what are the functions? What are the services that matter? I talked to some, without mentioning a name, I talked to some equipment provider and was talking, okay, I'm interested in the interface. What parameters can be exposed? And then they tell me, oh, 10,000. So and which one? I said, yeah, but which one matters? Which one? So I think there is much more research in the functionality and how to use the functionality, what to expose. You cannot expose everything. What is relevant? What is
exactly, yeah.
So that's why I need that we need some more end-to-end, that we need to interact, that we need this also multidisciplinary research to because if I don't get access to technology, to a good physical layer, I cannot do anything at the networking layer. So you need to and still at the physical layer, you can claim that you have the best technology with the highest promises in terms of capacity and speed. But if I cannot use it at the networking layer, how can you share it with multiple users? How can you say that it is energy efficient? Maybe per bit, you have the lowest energy consumption per bit. But if you cannot switch your radio off, and if you only need small packets, and if most of the time you have signaling and overhead and sounding and beamforming, what does it mean from an end-to-end point of view in terms of energy consumption?
Yeah, maybe I would like to take this point as maybe a final question to all of you, because at the event on Monday, there was also a board member of Deutsche Telekom, Mrs. Nehmert. She was introducing the vision of Deutsche Telekom, and she emphasized the issue of sustainability a lot. So, and when I look into the discussions on 6G, I was questioning, are we focusing enough on sustainability and this energy consumption, or are we thinking maybe too much about new functionalities? Just a question, maybe everybody can provide his view on it.
In my case, I mean, it's very simple because I go at it from machine learning. So typically machine learning usually is based on maximizing test accuracy, right? So now you can change the system design by now taking into account the energy, of course, of the compute and the energy of the transmission, which gives you a completely different type of performance, right? So yeah, I'm looking at that. Probably it's not enough, but yeah, I'm going at it from the green AI perspective. But again, you could look at it from material perspective, from, it's a multidimensional question, in fact, right?
Yeah. Maybe Ingrid?
Yeah, because mainly, generally efficiency is looked at energy per bit, but how do you measure? Because people tend to look only at the end devices, which are the battery empowered devices. And of course, there you optimize in energy efficiency. But if you look at the infrastructure, I think you blow up the infrastructure, you put much more software, much more cloud, much more whatever processing. Data plane has perhaps been simplified. You have the data plane where but then you create a huge control plane, and for some application, you transport much more bits than what you need for the actual data. So for me, we need to look, and have to look at the full picture, look at the whole end-to-end system, and look how many data bits, effective data bits, have been transported. And then you can calculate the energy consumption per bit, but not just from a radio technology. If you cannot switch off the radio, I think you can do optimization, because sometimes you have these wake up times, but you have to be careful because many components in a radio, they need stabilization time. So it's not that obvious. If you go for these high speeds, maybe you don't gain so much, maybe you cannot switch off anymore. I think there is many more that can be done to improve energy efficiency. But again, I think you will need multidisciplinary studies and kind of co-design to optimize it. And I have the impression that we still keep working in our silos too much.
I think we in 6Gem we were trying to do this.
Yeah, I know we had that discussion.
So maybe Harris can add something.
Yeah, I think it's an interesting discussion, but I think we should not be afraid to step away a bit from our own and look a bit more at the full picture to see where is the real energy consumption. Maybe I have a lightweight terminal, but I shift all the processing and all the energy in the cloud and in the edge and wherever in the control plane. You can do monitoring, but if you monitor everything, you will end up with a monster of a control plane. Is that what we want? I don't know.
Yeah, maybe Harris, what's your view on?
Well, if I tell you my view, I don't think that you will invite me again. So I have to, I mean, first you say, I mean, you mentioned the sustainability, right? This is the main point. I have to disagree with a comment from Ms. Nehmert, Claudia Nehmert, from Deutsche Telekom. I don't think that there is any issue with sustainability with communication systems. I think there's an issue with sustainability that they are introducing within their application domains, within the operators. So they are bringing their own data centers, more energy requirements, more everything in order to support their fighting against the Googles, Apples, Facebooks of this world. The first generation, second, third, fourth, fifth, and sixth eventually, we will end up with they are actually lean, more efficient, more elegant, I would say. So each generation is actually solving some of the issues that we have earlier, and then simplifying our architecture, simplifying our communication. Of course, the techniques becoming complex, but in general, architectures are getting simpler because our hierarchical structure is flattening. So if you look at that context, I really don't see why we have to address sustainability as a major criteria for communication networks, because we do not generate such issues or problems in the future for the future generations. For in any context, it is application domains that are generating. We do provide pipelines for those applications to run, but it is not our servers that are burning the energy of this world. So this is my opinion. Of course, I do agree that we will have to sit down and make this nicely in some report style and see how we are going to defend it or hear other opinions. But in overall, I really don't see that communication network, communication engineering is generating such energy consumptions that are so pushed out now to the highlighted to the sky.
I think probably it's the holistic view. Sometimes a little bit more communication can save a lot of energy in an application domain. So if you take a holistic view, it's worthwhile to spend some energy in the communications in order to save much more energy somewhere else. Probably that's also one way to tackle it. Thomas, you have the final word.
Also a few comments on that. Let's say when you look at from a terahertz perspective, then on the one hand side, the terahertz power amplifier, they become less efficient the higher the frequency is. So you waste energy. On the other hand side, you get a beam. So you don't transmit the energy in all direction. You focus, once you find the other beam, you focus on the particular user. That is nice. So that is in terms of energy efficiency beneficial. The last aspect there is you also hopefully, let's say we do not yet know, we do not fully understand yet, that you do not need equalizers. So equalizers also cost you power. You have to equalize the channel for that. And then you have protocol overhead on top, so you have to find the beams. So for us, you may remember on my last slide, I put energy efficiency in mobile devices in the foreground, because I really believe that that is key criteria for terahertz communication for mobile devices. I don't like to charge my smartphone working with terahertz each hour. Even let's say on the full climate crisis discussion, but also for customer convenience, energy efficiency is also very important. And in terahertz, it's really challenging. It's an open topic.
I think you mentioned the customer convenience.
That's a good point to build up a device.
Yeah. And I would like to underline that energy efficiency was always a topic in designing mobile radio networks, because we want to...
For the terminal, in view of the terminal.
Yes.
Yeah, it was focused on the terminal,
But I think less in the infrastructure.
Yeah, here is a funny story, but it's true. I talked to a person from Ericsson. They trying to, their goal was energy efficiency, turning on and off base stations. And guess what? They used machine learning to do that. The conclusion of the study was the machine learning power is more energy hungry.
Yes. But they want to inject machine learning everywhere. So I'm a little bit afraid that you end up with...
Okay, great. So there's a lot of work to do in the area of future communications. And I think that's the very good news for all of us in this area, that there's really a tremendous work to do. And therefore, we will have in the future, hopefully, lots of opportunities also to discuss these issues, and also hopefully in the future again in person. Therefore, to end this session, I would really thank all the speakers very much for their talks and their visionary ideas and their openness in this discussion. And I hope that this was also useful for the audience. And I thank also the audience for participating at this session. We will make the slides available for the session afterwards. And hope to see you soon in person. And thanks a lot again.
Thank you very much.
Bye-bye.
Thank you. Bye-bye.
See everyone.
Thank you.
Thanks a lot.
Bye.
Take care.